Good day, this is Jim Pytel from Columbia Gorge Community College. This is Digital Electronics 1. Today's lecture is entitled Fixed Function Integrated Circuits, ASICs and PLDs. Before we go into the actual specific functions of specific fixed function integrated circuits, let's just talk about some of the packaging for common fixed function integrated circuits. We're going to do a brief introduction to ASICs and PLDs. Okay, if I was to tell you in lab, Johnny, go to the lab bins and get me a NOT gate. What you do is, because you've been studying this course, you're going to run up there and start rummaging through the bins and start looking for something that looks like a triangle with a bubble on it. And you're going to be there all day because there are no triangles with bubbles on it. Okay, that is just the schematic symbol for it, very similar to a resistor, which is really a shorthand means of drawing something that looks like this with our color bands on it there. You can kind of see the parallel between the resistor schematic and the resistor real-ish representation I'm trying to draw there. There is no such parallelism for a NOT gate because it does not look like a triangle with a bubble on it at all. Okay, most of the time they're going to look like a black box. Okay, the black boxes that we're going to be using actually carry what's called a monolithic silicon chip in it. Monolithic means basically one piece. Okay, for the intents and purposes of this course, you don't have to know how they're hooked up inside. I don't care that you know all that stuff. I just need you to know how they work and what they do. Okay, so in your semiconductor devices and circuits course that you may be taking, or whatever it's called, power electronics course, you'll figure that out. Okay, but it's on a single piece of silicon, and it's just put inside a plastic or a ceramic carrier. Okay, and that's really what that thing is, that big old black thing. Okay, those pins on the outside are routed to that silicon chip. Okay, and these pins are the external interface to that. Okay, and then a plastic or ceramic cases over the top, and that is our integrated circuit. This one on the left, that's what's known as a dual inline package. Dual because there are two rows. Okay, they are aligned so that they will fit inside your protoboard, and additionally they are aligned so they are called through hole, in contrast to surface mount. Okay, which types of the technology do you think goes through holes? The through hole. Which type of technology do you think goes on top of a board? Surface mount. Okay, SMT, surface mount technology. Okay, the surface mount technology saves a manufacturing step. You don't have to drill a hole through it. Okay, you still have leads that need to be soldered, and in the one on the left hand, this one right here, you still need to solder those little wings to a copper lead. This one right here fits into a special socket, which is pretty cool. If you can imagine this little socket sitting on top of a printed circuit board, and all the connections to the outside world it needs is there, and that guy just kind of pops into the socket, and all its interfaces are on the side of the chip and the side of the socket. So that's pretty cool. You got to make sure the socket fits. Okay, this one on the furthest one on the right, it's what's known as a ball grid array. Okay, just like catching a frog and trying to see what the sex is, you flip it over, there's a bunch of balls on it. The reason why is, think about this, you're limited to the perimeter for the number of leads. As these things get incredibly more and more complex, you might not have enough area there. So why not make the whole area, the bottom of this thing, have all the connections? And again, this obviously requires a special socket or setting. The ones that we're going to be using the most in the lab is going to be this guy for our TTL circuits, and this guy. And no, we're not going to be taking that thing out of the circuit board. Our field programmable gate arrays, the programmable logic devices that we're going to be using, they're already mounted on the circuit board. Don't flip it over and see what the sex of this thing is. Okay. About the dual inline packages, what are the pin numbers? Okay, so that's the common question there. When you get a lab, you're going to get a data sheet for the particular device. Okay, and it's going to have all the pin-out diagrams on it. We'll talk about data sheets later, and we'll talk about them in lab. Okay, so one of the things too is the analogy I like to use is you're not going to build a house out of lumber that's 2.5 inches by 5 7/8 when you can just use a 2x4, i.e. a commonly manufactured piece of lumber. Okay, so the commonly manufactured pieces of lumber that we're going to be using a lot of is these TTL circuits that are in dual inline packages. And there are certain standards that are accepted. However, there are a number of different manufacturers and a number of different styles. Okay, so for a TTL, you're going to see something like an SN74LS04, or you might see something like a DM74LS04. Just ignore this garbage. Okay, it's not garbage too. This is really kind of the function. The SN and the DEM, those are different manufacturers, Motorola and Fairchild specifically, I think. Texas Instruments is another manufacturer. 74, it's the series. The 54 is the military, it's radiation hardened ceramic case, I think. 74 is kind of the commercial grade. LS, it's a style, it's a low power Schottky, whereas the non-Schottky circuits use more power, but you can switch them at higher frequency. Don't worry about it. The 04, and we're going to go into these things in a little bit here. That's an inverter. Okay, it's got a number of inverters packaged on that monolithic circuit. And when I say it's not just one inverter, it's a mass manufactured. There are a number of inverters on it. The deal is, do not remember these numbers. I don't remember these numbers. I just look them up. Okay, if I need some NOT gates, I look up the number in one of the TTL manuals that we have. There's this thing called the internet. Perhaps you've heard of it. You might be able to search for things. Okay, so there's standard part numbers. There's also pinouts. Okay, so how am I? There's a bunch of pins on these things. They look like fat centipedes. Which is the pin? What's the in? What's the out? Well, you're going to look at a data sheet, and it's going to tell you what number that pin is for an in or an out or a clock or whatever. Okay, what's the pin number? So, easiest way to identify these things, they all have an identifier. Here's my chip. Okay, I'm going to go ahead and say, Johnny, get me an inverter. You're going to go ahead and go to the 7404 drawer. You're going to pull it out, and you're going to look. And there should be 7404, and I'm trying to write sideways, in exceptionally small letters on it. So what you want to do is make sure that you go ahead and pull out the magnifying glass and the light. Make sure it really is a 7404. Make sure it's got the correct number of pins. Make sure it doesn't have pins snipped off of it. Make sure it doesn't have any melted marks on it or burn marks on it. Make sure that the pins are not bent there, because you know who previously used that before? Maybe you. You got frustrated, it fell on the floor, you may have stomped on it, and you may have put it back in there. Long story short, good lab practices, guy. They all look the same. They all look like that thing. It'd be so easy for you to grab a damaged one or the wrong one or put him in the wrong drawer. So standard operating procedures, pull it out of the drawer, make sure it's got the correct pins on it, make sure they're not damaged, check the number on it, put it in the chip checker. The first lab I'm going to show you guys how to use the chip checker, because there's nothing more frustrating than working on an entire lab and realize your chip was always damaged and never would have worked. The other thing is standard operating procedures for the close down of lab. Make sure you put that thing back in the same drawer. Clean up, because you never know, it might be you that receives the damaged chip the next time, or the wrong chip. One brief note while I'm on these pins. One of the most complicated troubleshooting experiences actually occurred the first time I ever taught digital electronics. The guy had his circuit all set up perfectly, and it was not functioning correctly. This is what happened. Like I said about the Protoboard, and we're actually going to go talking about the Protoboard in a little bit here. he had placed these things in the holes rather forcefully, and all of them went in except for this one. It rolled underneath itself. He had the whole circuit set up correctly, and that chip looked like it was inside there. Always look at these things from the side. It took us a while to figure that thing out, but we had a good laugh about it after a good hour or so troubleshooting it. Actually, not an hour, but I thought that was a pretty good point there. Make sure, just look at these things from the side too. Okay. All right, let's go back to pin numbers. All right, there's an identifier always on chips. If they're plastic, unfortunately, they've got like these little pore marks here. Those aren't the identifiers. It's a notch. You can even see that on this one. There's always a notch. Sometimes they even have actually the numbers on them. Okay, the notch, that's the top. This one, that's number 1. Okay, so the upper left, and by the way, the centipede's legs are pointing away from you. The upper left, that's number 1. Go counterclockwise in increasing order. Okay, they're typically 8s, 14s, 16s, 18s, or 24. Always even number, obviously, because there's pair. Okay, so let's go ahead and do a quick quiz here on what the pin numbers are. Okay, what's that guy's pin number? Give you a little second here. So, if the upper left, that's 1. And by the way, the legs are pointing away from me because I'm looking at the notch, obviously. 1, 2, 3, 4. That is pin 5. Okay, here's another quick one. Okay, what pin number is that? So I'll give you a little bit here. And trick question, it's 5. Because my identifier is right there. All I did was just flip the chip upside down. So 1, 2, 3, 4, 5. Okay, so you should be able to, in any orientation, figure out what the pin numbers of these things are. If I give you a number, you should be able to point to the pin. Okay, so and it's critical to your use in the data sheets. You should be able to do this thing sideways, upside down. You should be able to do this underwater, inside a pool, blindfolded. Okay, to close out some of the key topics in this lecture, before I start wandering, is this concept of ASICs and PLDs. Okay, so some of the fixed function integrated circuits, you know, it's the scale of these things. The NOT gate, the AND gate, the 7404 is a NOT gate. It's not the most useful thing because it doesn't have any other functions besides the NOT gate. At some point, what you're going to do is you're going to step up the scale. Okay, you're going to need a little bit more I guess logical computing power. Okay, so you're going to use a NOT gate in conjunction with an AND and in conjunction with an OR. Pretty soon you're going to have a bunch of these dual inline packages taking up a lot of space on a circuit board. Okay, so then what you're going to do is you're going to step up to what might be is an SSI, small scale integrated circuit, MSI, medium scale integrated circuit, so on and so forth. You're increasing the complexity of these things. Okay, and finally you're going to get to the point where you have created the circuit you want. You want to create an application-specific integrated circuit. Okay, and for the general scheme of an application-specific integrated circuit, and kind of be, I guess, summarized as it's a custom-made fixed function. In the example of our nanobot factory, let's say you want to have another nanobot factory that does the exact same thing, and you want to have another nanobot factory. Pretty soon you realize the cost of all those little chips in there might justify you actually making a specific circuit for your factory. Okay, so that's what you're going to do is you're going to go to an ASIC vendor and say, hey guys, I want you to make me this chip. And you're going to go through an expensive test and verify, and they're going to go ahead and mass produce an expensive chip for you. And that's going to be awesome because it's going to be optimized for your particular use, and it's going to do your job exceedingly well, that one function. And next year, when you want to go ahead and upgrade the factory, or if you want to change the factory, how it works, you're out of luck because you've sank a lot of money into this application-specific integrated circuit. Okay, so that's the way business has been done for a lot of time, for a while. And then there's these things called PLDs, programmable logic devices, which have really changed the face of digital electronics. What a programmable logic device is, and they're, for the intents and purposes of this course, I'm going to kind of divide them up into SPLDs, simple programmable logic devices, CPLDs, complex programmable logic devices, and FPGAs, field programmable gate arrays. What they are is a device that you can buy. Okay, whereas this, you require an ASIC, you require a vendor. A PLD, you can buy a PLD off the shelf, and what happens is it's a blank slate with a bunch of programmable logic elements in it. And what's neat about this is some of them are reprogrammable. So you go ahead and create this nanobot factory circuit that you want to go ahead and keep on using over and over and over again, and you program it onto one of these programmable logic devices. And then in a year, when you want to go ahead and upgrade your factory or change the function of your factory, you reprogram that device. So these things are of an amazing advantage for keeping companies competitive. Okay, so I've got the major thrust of this lecture done. I do want to go into some lab practices. I'm going to have a whole section on lab instrumentation as applied to digital electronics, but while we're on the topic of dual inline packages and protoboards and lab practices, just let me mention a couple brief things. I already mentioned check it, test it, put it back. I already mentioned about putting them into the protoboard. One thing too is just Basic Electronics 1. Those rows in the protoboard are electrically connected. For the protoboards we use in 5 pins. That forms a node. Okay? Columns are not connected. Okay? So if I took a chip, I want to place it across one column to the next column, bridging those columns, because this might be an in for that pin 1. And let's say it's in this particular case, it is a 12 pin. So pin 1 is an in, pin 12 is an out. It would make no sense whatsoever if I took that device and electrically connected pin 1 to pin 12. I don't put them in the same column. It's not going to work. Okay? Because 1 and 12 have to be separated. Okay? They have to be electrically disconnected from each other. So what's neat about this here, this arrangement, I can put any number of wires I want to into that row. I can put any number of wires into that row. Okay? There is this thing called a dual inline package switch. Okay, it looks just like a dual inline package chip. It's got its package and it's got its leads. What it is, it's a bunch of single pole, single throw switches. Which position is the switch open? Which position is the switch closed? I don't know. You tell me. This is the stuff I was talking about earlier. This is digital electronics. That stuff right there is basic electronics. Okay? So when I hand you a dual inline package switch, you have to know that an open switch has incredibly high resistance across it. A closed switch should have incredibly low resistance across it. And don't be the guy that takes those things and puts them into a single column, because, as we said, is those rows of 5 on a protoboard are electrically connected. It would not make sense to have this electrically connected row and put a switch in parallel with it, because Johnny conventional current electron is going to enter this end and just keep on going. Whereas, if I'm placing that dual inline package switch from row to row, Johnny conventional current electron is going to enter. Oh, he can't because the switch is open. Now you close the switch, and then he can get from there to there. Okay? So, just a brief reminder of how these switches work. Like I said, it's not intense basic electronics, but you should know the difference between an open switch and a closed switch. You should understand electrical connectivity. You should be able to figure out what is connected on the protoboard, what is not. We're going to go back into some of the how to use a protoboard efficiently for digital electronics. This concludes this portion of the lecture. Let's go ahead and actually dive into one of the specific fixed function integrated circuits we'll be using a lot of, the NOT gate.